We are ESE Senior Design Team 4, and our project is the Emergency Entry Logistics System. Our goal is to collect crucial information that will help firefighters save more lives. In this video, we'd like to discuss the technical design of each subsystem of our project and then show how we pulled it all together for our working demo. For that purpose, we've broken our system down into 5 components: the module enclosure, Bluetooth tracking, IoT communications, cloud backend, and the user interface. The primary considerations when designing the modules were reliability and safety, meaning all components had to be rated for use in extreme temperature environments. In the event of direct exposure to a fire, we had to ensure that our system would fail safely. For that reason, we decided to use non-lithium batteries, despite marginally lower performance and energy storage, due to safety concerns. These batteries, as well as the power adapter board, the main board, and the antennas, would all be safely housed in an insulated enclosure measuring approximately 8 inches by 6 inches by 4 inches. In the interest of scalability of production and ease of installation and maintenance, we opted for a 3D printed design with a lid attached by screws to ensure a tight connection. For a material, we selected Ultem, a high-strength plastic with excellent heat deflection, which is self-extinguishing as well as electrically and thermally insulating. All features which could help protect the components inside. We would use gasket foam on the lid as well as around power and antenna cables to ensure a watertight seal and help reduce smoke exposure during a fire.
The tracking system has 2 components: ID cards and tracking modules. The ID cards are given to each employee and continuously broadcast their unique identifier. The tracking modules are distributed throughout the building and communicate with each other over a mesh network. When they receive a message from an ID card, they forward the UID and receive signal strength to a cellular-enabled module on the network. This module acts as a gateway between the mesh network and AWS, where the data is processed. We designed the modules to be custom-built PCBs. However, due to the COVID outbreak, we had to use the development boards for the microcontroller instead.
Each node in our system contains a custom PCB that houses power management, communication modules, and antenna routings. Under normal conditions, the boards are powered by tapping into 120 volts AC. That is passed through an off-board AC-DC to convert it to 12 volts DC. From there, the 12 volt is split and runs to 2 different linear regulators to convert it to the 3.3 volts and 1.8 volts that the various components run off of. In addition, there is a battery that is able to power the entire board for upwards of 4 hours in case the AC power is cut during an emergency. The linear regulators were chosen to function with both input voltages, 6 volts from the battery and 12 volts from the AC-DC. The 2 modules on the board are the BLE microcontroller hybrid with thread communication and the Cat-M cell radio. Both transceivers are powered by 3.3 volts. However, the Cat-M radio uses 1.8 volts for its onboard communications, so 3.3 volt to 1.8 volt level shifters were needed so the 2 modules could interface. The Cat-M module also needs an active SIM card to function properly, so there is a SIM card holder on the board. Since both modules required off-board antenna, RF signals needed to be routed from the modules to onboard coaxial connectors. From there, wideband omnidirectional antenna allow both the Cat-M module and the thread module to communicate out. A microstrip design was used to match impedances and maximize power output.
There are 3 core components to our AWS cloud infrastructure. The first of these components is IoT Core, which allows for secure and lightweight message transmission and routing, and serves as our base endpoint for cloud communication. IoT Core is highly scalable and makes it easy to onboard new devices while maintaining low overhead communication through the MQTT protocol. Both perfect fits for our system constraints. Once data is received from the hardware through IoT, it is piped through various rules to other services, primarily to AWS Lambda, our second component. Lambda allows for serverless, responsive communication, letting us do all the computation we need without requiring a persistent server. We trigger Lambda functions to help process data as it arrives, to do triangulation calculations in order to calculate position data, and to trigger on-demand processes. Once Lambda functions have processed and split incoming data, that data is stored in our third and final primary AWS service, DynamoDB. Serving as our cloud data storage, Dynamo is well suited to frequent small data writes and reads, and is integral to our solution. Data is stored in various different tables, from raw beacon RSSI values in the beacons table to high-level serialized floor plans in the floor plans table used for our UI. Together, these three components, cloud storage, computation, and communication, allow our system to be easily deployed, efficiently operated, and robustly scaled were our solution to reach deployment.
With all the mechanisms for data generation, upload, and processing in place, we now come to the highest touch portion of our project, the user interface. UI has two major parts in our project, floor plan consumption and heat map visualization. For floor plan consumption, site managers are able to directly feed the system a floor plan. Using click and drag features, the system processes the floor plan and stores it for display as well as for future calculations using user-defined rooms. For visualization, this data is then taken from our backend and from AWS and visualized for users as a heat map with the number of people in any given room corresponding to the intensity of that room. All of this is done using very well-known web technologies. Visualization is done through Fabric, which is a powerful JavaScript canvas library, as well as tools like jQuery, Bootstrap, and HTML5. With a backend built in Node.js, we have a huge amount of flexibility as to how all of this technology can be integrated, as well as significant familiarity for our users, which is extremely valuable when our core offering to site managers and to first responders is the ease of information presentation. We need this data to be very accessible, very visible, and simple to understand. And with the system we've built here, we can do that. With our core technology explained, we now have the ability to see them working together in a demonstration of the entirety of the EELS system. Thank you. Unfortunately, due to the current constraints, namely around building access, we were unable to fully integrate our system into one of the buildings around campus. The demonstration you're seeing now is one which portrays our ability to locate and track a person using just BLE in proximity to one of our nodes. This data is real data pulled from our AWS backend that was uploaded by devices running our code outside. You'll see as Damien moves around, we are able to track his approximate location and movement, and in the event that we actually had rooms, we would be able to assign him to a room. Despite the slight inaccuracy and jumpiness of the model, which you're seeing now, this is perfectly tolerable. This is because of the fact that we only need to locate a person within a room. We don't need specific locations like those granted by ultra-wideband technologies. So this slight inaccuracy allows us to be vastly cheaper and significantly lower power than other location options, enabling us to perform our tasks effectively and at a much lower cost than other parties.